time for us to go and do some applications involving parameterized curves. As we go through and do these applications, you're going to get a certain sense of deja vu. It's like, this feels a lot like what we did before, because it's going to be a lot like what we did before. The only difference is that while our individual pieces remain the same, we just have to think about, okay, how do we write that part? And so with practice, you'll see it's very easy to adapt to this new setting. Of course, it's important to practice, so do as many problems as you can. If you're following along with the video, make use of the pause button. See a problem you like, pause it, and try it out. See how you do. And if you ever need any help, I'm there, just unpause me, and we'll figure it out. All right, well, let's begin. Our first problem, find the arc length for the parameterized curve, where we have 7/3 t cubed plus t, 2/3 2t squared plus 1/4 to the 3/2. And time goes from 0 to 2. So we'll start by saying, all right, well, what is the generic formula? Now for arc length, our generic formula is the following. We're adding up from start to finish a square root of x prime of t squared plus y prime of t squared dt. That's our generic formula. What we should be thinking about is, in essence, this is capturing sort of the rate of change of how the particle is moving. See, the x prime, that's the rate of change in the x direction. The y prime, the rate of change in the y direction. So the square root of x prime plus y prime, that helps us get the diagonal direction. And that's the rate of change in the diagonal direction. So, of course, rate of change times the amount of change in our input. That's our change. So that's the length of a little part. We add them all up. That's the full length. Okay, so that's the formula. So we have our pieces. This is our x, and this is our y. The most important thing is, remember, we need to take derivatives, and we need to square them, and of course, respect the square root. We always have to keep in mind that square roots, they're not our enemies per se, but they are a bit of an obstacle. We have to make sure that we follow the rules of square roots. And so we're going to look for things such as common factors to pull out, or maybe some, if we're lucky, square on the inside. Well, we won't know until we dig into it. So that's why we have to get going. So for our case, we'll have our length is integral a to b. Well, let's just say what they are. 0 to 2. Okay, so 0 to 2. Square root of. Okay, so take our derivative. So 7/3 t cubed, it'll become 7t squared, derivative of t, 1 squared. Interesting. Now, plus, there's a 2/3. The 3/2 comes down. Then we have 2t squared plus 1/4 to the 1/2 power times the derivative of the inside. Remember the chain rule. So that would be times 4t, and all that's being squared. What an expression. Now, I will say, generally speaking, on these types of problems, probably about 80% of it is figuring out the square root, what's going to happen. So let's dig into that. So we got to simplify the inside. We'll start by squaring. In other words, we're going to expand everything out. And once we've expanded, we'll collect everything together that needs to be collected together. And then we'll start and go, what happens next? So let's do our expand and collect. Squaring it out, we've got 49 t to the 4th, square the first term. You have the cross term. Don't forget you're going to double. So 14 t squared, and then 1. Okay, here the 3's and the 2's cancel. That's some good news. And when we square, well, because this is to the 1/2 power, when we square it, it'll just become to the 1 power. So 2t squared plus 1/4. When we square here, don't forget to square the 4 as well. So that becomes 16t squared. Okay, so that's the inside. Let's continue forward, cleaning up. Whoop, I put a 2 there. That should be a 4. Sorry about that. So, all right, t squared squared. So 49 t to the 4th plus 14 t squared plus 1. Multiply the 16t squared through. 2 times 16 will give us 32 t to the fourth. 1/4 times 16 will give us a 4. All right, well, interesting. We combine the t to the fourth, so that's 81 t to the fourth. We combine the t squareds, that's 18 t squared, and then there's a 1. All right. Now, oftentimes when we see three terms, or something plus something plus something, we think, well, that's kind of like a square. Squared has three terms, right? So we just have to think about, okay, what would it be? Well, we're thinking of it and say that first term, that 81t to the fourth, maybe that's a square term. So this would be, if we are thinking of it, as 9t squared squared. The last term would be 1 squared. Now when I talk about the first term, the last term, what we really mean is you think about grouping things by the size, the degree here. T to the fourth, t squared 1. And you put them in the right order. So, is it a square? Well, if it's going to be a square, then we need the middle term to be 2 times the first term times the last term. And, lo and behold, it is. Aha! So this is 9t squared plus 1 squared. Okay, so all we've done so far is the most of the work. But what it is we've said this inside expression, when you carefully follow the algebra, and if you're nice to the algebra will be nice back. When you work it all out, it's a perfect square. We're taking the square root of that, so now we're ready to update. So our problem becomes the integral 0 to 2 of 9t squared plus 1. And that is something we can actually work with. The integral of 9t squared, well, you add 1 to the power, so that would be t cubed, divide by 3. So that would be 3t cubed plus integral of 1 is t. Go from 0 to 2. When you plug in 0, you get 0. Plug in 2. 2 cubed is 8 times 3. Well, that would be 3 times 8, 24 plus 2, giving us 26. And that says that the length of our curve from time 0 to time 2 is 26. Now, we don't have any units here, so it's whatever the units are being measured in. Oftentimes, we won't worry too much about units. In some sense, units take care of themselves. So whatever the units should be, as long as your input units are set up correctly, then the output units will match as well. So, there we go. All right. Beautiful, beautiful. A nice start. Really clean, simple answer. Those are the kind of answers we like, by the way. Clean and simple. All right. Well, we will keep going. So let's do another problem. And it looks like, yes, another arc length problem. So, find the arc length of the parametric curve. Okay, so we kind of know how this works. So we'll just start. What do we have? Well, this first piece is our x, and our second piece is our y. So if we want to find the arc length, what do we do? Well, we're going to add up, start to stop, of the square root of, and now we take the derivative of the x term. This is going to be interesting. Okay, well, there's a t plus 1 is e to minus t, so we need to do a product rule. So the derivative of the first would give us just the 1 here times e to the minus t. So 12 e to the minus t plus derivative of the second, well, the t plus 1 stays as it is, and the derivative of e to the minus t would be minus e to the minus t squared. Okay, that's just the derivative of the first piece. Plus, now the derivative of y. So plus derivative of 2t cubed, 6t squared. Derivative of 3e to the minus 2t, well, minus 6e to the minus 2t. Okay, squared dt. Good, good. Now we proceed. And of course, the main thing to focus on is the inside of the square root. That's going to be where most of the work happens. So we're going to start focusing on that. Well, what can we do? Well, let's start with this first term. We'll expand it here. So we have 12e to the minus t. That's fine. Now we can distribute. So this would be minus 12t e to the minus t. And then if we go to the second term, it's minus 12e to the minus t. Okay, squared. And, well, then we have this term, which there's not much to do on the inside. There's just, we'll get to the squaring in a second. But we say, ah, something nice has happened. Notice in the first term, we have three terms, but the first and the last cancel. Wow, almost as if it had been planned, because it was planned. Well, good. Now, time to square. So it becomes pretty straightforward to square. The negative goes away because you square negative becomes positive. 12 squared, 144. T squared, and here be e to minus 2t. Now, over here, well, there's a little bit more that has to happen. We'll have 6 times t squared. That'll become 36 t to the fourth. Then the cross terms. Well, 6 times 6 is 36, and then double that will be minus 72. Then you have the t squared and the e to the minus 2t. And then, on the end, it'll be 36, e to the minus 2t squared, e to the minus 4t. All right. Well, good. Progress. Progress. Now, what happens? Well, we look and say, hey, wait a second. Some of these terms combine. And in particular, we see that this term from the first expression combines with that term. And actually, they're very, very similar. So it's a positive 144 and a negative 72. Well, it turns out 72 is half of 144. So we say to ourselves, well, that's great. So that combines 36t to the fourth plus 72 t squared e to the minus 2t plus 36 e to the minus 4t. All right, well, we see a couple of terms, and we think to ourselves, it would be nice if it was a square. Well, is it? Does it work? Got to think about it. Now here, we say, this expression that we currently have, 36t to the fourth plus 72t squared e to the minus 2t plus 36e to the minus 4t, is amazingly close to the one right above it. Amazingly close. So close, it's just one small difference. The plus versus the minus. That's it. That's the only difference. Well, where does that come from? Where did this minus come from? Well, the answer is it came from the fact that this was minus. If it had been plus, it would have been a plus. So, okay. So what we can see is that our current expression is also a perfect square. And in particular, what it is it's the perfect square of 6t squared plus 6e to the minus 2t squared. Essentially, we've just changed a minus to a plus in the middle. That says instead of a minus b squared, a plus b squared. And now we're like, exactly in the place we want to be. Because we're ready to take our square root. Because we have a square root of a square. So, we have that our length becomes the integral. And I marked a and b. I should have said 0 and 1, of course, because those are our bounds. So 0 to 1, the square root here, that squared, of 6t squared plus 6e to the minus 2t dt. Well, all right, not too bad. Integral of 6t squared, well, we have a t cubed, and then divide by 3. So that would be 2t cubed. Integral of 6 e to the minus 2t. Well, you will have a minus 3 e to the minus 2t. Now, where is that minus 3 coming from? It's 6, but you have to divide by negative 2 to accommodate the fact that there's a minus 2t up in the exponent. So, there we go. And then evaluate 0 to 1. Well, so what is that? Plug in 1. You get 2. And then here, minus 3e to the minus 2. Okay, are we done? Don't forget to plug in 0. See, so often when we plug in 0, we get 0. Sometimes we forget to even do it. But we can't forget. You got to do it. And because maybe it won't be 0. See, let's look. Plug in 0, you get 0. And you're like, ha, Steve, it was 0. But wait, there's another term. Here, e to the 0 is 1. So it's minus 0 minus 3. So really, this minus 3 makes it a plus. So we end up with 5 minus 3e to the minus 2. And there we go. There we go. Now, I will say on both the problems we did here with arc length, it was the case that we got a perfect square. That's oftentimes one way to approach it. It's not the only thing that can happen. Sometimes you might have things that pull out. Sometimes you might have things that just work out cleanly. You don't know unless you do the problem. But as always, respect your square roots. Be kind to them. And don't do anything that's algebraically bad. Don't commit the mortal sin of the square root of a plus b is the square root of a plus square root of b. So many people do that. No matter how many times we tell our students it's not true, they don't believe us. I hope you believe us. All right. On to our next problem. Find the area inside the region enclosed by the parametric curves. Well, it's really a parametric curve. That's not two curves. It's one single curve. 1 minus t squared, t minus t cubed. And it even gave us a picture. So we say, okay, so that's what we're trying to look like. So, what can we do? Now, let's be careful here. Because when we're looking for area, there is a little bit of sort of mischief that can happen when it comes to orientation. So it's not enough for us to know the curve. We should also think about how do we move on the curve. So let's think about what's true. So suppose we were to plug in, say, a large positive value. So in other words, where are we at as we head off to infinity? Because there's really two things that could happen. We could be coming up, loop around and keep going up, or we could be going down, loop around and keep going down. So one way to figure it out is just say, what happens in the long run? Well, let's think about our y values, because in essence, the up-down seems to be the driver. If I plug in a large number, well, the t versus t cubed is going to dominate, which means that for large values, I'm going to be negative. Well, okay, that means as time goes on, I'm going to be down here. If I plug in a negative number, see, a minus cubed, it's going to make a minus, and there's a minus there, which means that for negative values, large negative values, I'm up here. So the way we move on this curve is in the following. So this is important because we want to take into account orientation. Now, let's suppose we accept that this picture is accurate and we say, hey, there's some symmetry here. So in other words, you pick it up, put it down, it's the same part. So we could say, let's just find half of this. All right, that's perfectly fine. But if we're going to do that, we need to know a couple of things. For instance, when do we start and when do we stop? So how do we do that? Well, let's think about some key locations. Here we see we're hitting the origin. So when are we at the origin? Well, we're at the origin when 1 minus t squared would be equal to 0, or t squared equals 1, or t equals plus minus 1. So what happens here is we come through at time -1, and then we come back again at time +1. Where are we over here? Well, over here, what's true? Well, we're hitting the x-axis. So when does t minus t cubed equal 0? Well, we can think about that. T minus t cubed equals 0. That's the same as t times 1 minus t squared equals 0. Well, we already know about 1 minus t squared equals 0. That's the origin. So the other time is t equals 0. So we come through time -1 to the bottom half, to the top half, and we go back out. All right. Well, if we think of our little rectangle here, what would we have? Well, we have the following. This is saying we're going to add up, start to stop, and we're going to do our height and our width. Okay, so that's how we find area, height and width. Perfect, easy, right? So what's our height? Well, if we're slicing in this way, our height would be what? Well, it would be our y of t. What about our width? Well, our width is how far across we are. Now, take into account orientation, because we're sort of going in the wrong way. See, we're going from left to right as we move along the top part. So our width, normally we'd say it's x prime of t dt, but because of orientation, we need to correct that. So there's a negative x prime t dt. All right, now finally we say, okay, good. So we're going to double, because we're only doing the top half, integral 0 to 1, and then we have our pieces. Our y of t, t minus t cubed, then we take minus x prime of t. Well, that's going to be a minus, and x prime of t is a minus 2t dt. All right, well, what does that give us? So we have 2, integral 0 to 1, minus minus makes a plus, so distribute through, we're going to get 2t squared minus 2t to the fourth dt. And that gives us 2, then we're going to have 2/3 t cubed minus 2/5 t to the fifth. Evaluate from 0 to 1, and that will be what? Well, really, you can say, hey, factor out this 2, that's 4. Then you have 1/3 minus 1/15. Sorry, 1/3 minus a fifth, put into 15ths. 1/3, 5/15. 1/5, 3/15. So that'll be 2/15 times 4, leaving us with 8/15. And there we go. There we go. Great. That's the answer. Now, you might say, what about the part below? So this part, what would be the right integral? Well, notice if I'm down here, what happens? Well, now the x prime of t dt, see, it's going in the right way. I don't need to correct the sign. So on the bottom part, it would be x prime of t dt. But what happens? Notice the y value. So that's now negative. So to get the height, I have to multiply negative y of t. So it turns out that on the top part, there's a negative because of the width. On the bottom part, there's a negative because of the height. So we could have just integrated from -1 to +1. We would have still gotten the right answer. But where the negative shows up is for slightly different reasons. Now, we're going to do this one a second time. The second time is even cooler, because when I first saw this, a student was saying, I tried it and I got the right answer. And I was like, you did? That's amazing. I don't know why. And then I saw it and I was like, this is so cool. So hold on. This is going to be so cool. And what we're going to do is we're going to integrate where instead of thinking about going down to the x-axis, we're going to think about going across to the y-axis. And we're just going to naively set things up. We say, okay, we see where we need to start and stop, -1 and +1. So here we go. Integral -1 to +1. And then we're going to have our width. So we're thinking about here our width. Let me switch to a different color just so we can really highlight what's going to happen here. So our width will be to the axis. And what is that? Well, that's going to be x of t. And our height, well, that'll be our, up and down. That's going to be our y prime of t dt. Okay, so let's just integrate that. Let's see what happens. And see if we get a similar answer. And then we're going to have to say, how in the world did that happen? That's the cool part. That's the cool part. Okay. All right. Oh, I'm getting too excited here. Let's make sure we get the same answer first before we get too excited. All right, Steve, calm down. Calm down. Okay, so what is x of t? 1 minus t squared. All right. What is y prime of t? Okay, that would be, take the derivative, 1 minus 3t squared dt. And at this point, they don't look alike at all. Looks can be deceiving. Okay, so this becomes integral -1 to 1 of, multiply it out, you're going to get 1. Then you're going to get minus 3t squared minus t squared. So that's minus 4t squared. Then plus 3t to the 4th. Okay, so that's the expansion, dt. You should always make sure you include that. It's good practice. It's good notation. Good notation is important. All right, what does this become? Well, this becomes, when we integrate, t minus 4/3 t cubed plus 3/5 t to the 5th. Evaluate -1 to 1. So, when we plug in 1, this is going to give us 1 minus 4/3 plus 3/5. Subtract, when we plug in -1, well, minus 1 plus 4/3 minus 3/5. In fact, you see that there's a symmetry. So really, if we understand this, we just double, and that's our result. So, in terms of common denominator, 15ths, what do you have? You have 15 15ths. Here, you have to multiply by 5. Minus 20 15ths. Ooh, that's pretty big. Here by 3. 9 15ths. And distribute the minus through. So plus, same thing. 15 15ths minus 20 15ths plus 9 15ths. And 15 plus 9 is 24. Subtract 20 is 4. You get the same thing here, leaving us with 8 15ths. The same answer. Okay. Now, so far you're like, okay, so what? But look at what's happening here. Notice this rectangle that we drew. It's coming all the way in, right? So, when we're using these rectangles, what ends up happening is that we're actually somehow using these pieces as well. And that's probably making you say, wait a second, how is it we got the same answer, but we also had these pieces showing up? So this is where it gets fun. This is where it gets fun. So our picture is getting a little bit crowded, so we're going to redraw it just so we can understand what happens, because there's something beautiful. All right, we come down and we loop. And I'm going to mark the orientation again. We only really need to see what's happening for one part to really get a clear picture of what's happening here. So when I'm coming along this top part, so let's say, I don't know where the peak is, so let's say it's here. So that's the highest y value. So when I'm coming along this piece here, what happens is I'm going to compute the area all the way to the x-axis in this sense. And when I compute that, that's going to be a positive because I have x and y prime is positive. So it's positive area. Now, from the peak down to here, what happens? Well, what happens is I'm going to now go from the curve to the origin. So I'm going here. But what do you see? Well, now, because I'm going down, y prime is negative. So this will be a negative contribution there. Notice that this piece of area ended up being computed twice. In one time, we got a positive contribution. The other time was a negative contribution. They cancel each other out. So that when you do the whole thing, the only thing you're left with is this area that only got counted once. And so even though it feels like it shouldn't work, it automatically takes into account the right changes. And in general, this principle works for any curve. If you have any curve that self-intersects and you want to know the area, you just integrate start to stop, either y prime times x or x prime times y, and just pay attention to the sign. Everything works out beautifully. And even though it feels like, this area is going to be wrong, when you dig into it, you see, oh wait, the pieces cancel out exactly as they should, and I get the right thing in the end. Math is beautiful. That was so cool. When I finally realized what was happening, I was like, wow, this is so cool. It's even cleaner and better than I would have thought. Good times, good times. All right, well, we should do some more. So let's try another problem. Surface area. Find the surface area, which results from rotating the parametric curve. X is log of secant plus tangent minus sine, and y is cosine around the x-axis. Well, what a strange looking curve. I don't know exactly what it looks like, but we don't have to know. It's doing something, so I'm not sure exactly what it does. Let's just say it's doing something like that. Okay. Probably not, but who knows? And we're spinning it around the x-axis. Now, how does surface area work? Well, surface area has a very clean formula if you think about a very generic sense. You add up, start to finish, 2 pi, radius, and length. And that's the formula. It's the same formula regardless of what setting we're in. Well, what do the pieces represent? Well, here, the way we think of it is we take our curve and we chop it into parts. We're going around the x-axis, so our radius is how far we are from the x-axis, and this piece here, that's our length. And so if we can understand what is our length and what is our radius, life is good. All right, well, time to think about those parts. The radius is probably the easiest thing to figure out. So that is the distance to the x-axis. And what is that? Well, it's y. So this is simply going to be y of t, or really cosine of t. Okay, so the length, that's the hard part. Well, the length is like the arc length. Square root x prime squared plus y prime squared dt. So we're going to take some time to really dig into that expression. That's going to be the one that takes us probably the most amount of time. So let's start taking our length. So we have the square root of, Now, we've got to take the derivative of x. The derivative of log secant plus tangent. Now, that's not just a random expression. We've seen log of secant plus tangent before. If you start combing through your memory, you say, wait a second, what was that? Where did it show up? It shows up in the integral of secant. So if you integrate secant, you get that weird expression, log of secant plus tangent. Okay, so if you take the derivative of log of secant plus tangent, the result is secant. So the derivative of log secant plus tangent is secant minus the derivative of sine is cosine squared plus derivative of cosine, negative sine squared. Okay, so that's going to be a piece that shows up in our length. Now, the good news is it's gotten better. You see, when you first see this problem, you're like, log of secant plus tangent, So the girl's like, still not excited, right? Because there's all these pieces floating around. But we're not done. We're not done. So let's see what we have here. So we square. So when we square, secant squared, all right, that's easy. Now, secant times cosine. This is where it's good to remember how secant and cosine connect. Secant is 1 over cosine. So secant times cosine is 1. So we're going to get secant times cosine, which is 1. Don't forget the minus. And because it's the middle term, there's going to be 2. So that actually just becomes minus 2. Very clean, very clean. Then plus a cosine squared. And then here, you square that. The minus goes away. Sine squared. Beautiful. Wait, cosine squared plus sine squared, we know that. Cosine squared plus sine squared is 1. So all of this combines together to give us minus 1. All right, great. Now, secant squared minus 1. Well, the problem is that's still underneath the square root. We'd really like to get rid of that minus in the middle. How do we do it? Well, this is not a case where we can write the inside by somehow factoring it as a square, but maybe there's a trig identity that we can use. So we start looking through our trig identities. Is there some trig identity that involves secant squared? Well, you're probably going to guess, yeah, of course there is. There's always a trig identity. It's knowing which trig identity to use. And in our case, there's really only about a half dozen that we need to know. We've already used one of them, cosine squared plus sine squared equals 1. That's actually related to another trig identity that says the following. Namely, if you divide the expressions here by cosine, you get 1 plus tangent squared equals secant squared. So that comes from sine squared plus cosine squared equals 1, just dividing through and cleaning up. Or, put a better way for us, secant squared minus 1 is tangent squared. Aha, aha. Good. So it turns out that our expression underneath the square root can be written as a square. It becomes tangent squared. Ah, nice. All right, so let's see where we're at. So what do we have? Our surface area is we're adding up a to b, so we do it for our time, 0 to pi over 4, 2 pi, and then we have our radius, which is cosine of t, and then our length, well, it's the square root of tangent squared, is tangent of t. Okay, so that's what we have to integrate. Now, what happens next? Well, we've got to figure out how to integrate cosine times tangent. Well, we don't, but maybe we can rewrite it. Tangent, this piece, is sine over cosine. And lo and behold, we have a cosine. They cancel out. So this becomes the integral from 0 to pi over 4, 2 pi of sine t. Great. Perfect. That's the kind of integral we like because it's one of our basic things we know how to integrate. So we have our 2 pi. The antiderivative of sine is minus cosine. Yeah, don't forget. It's one of those really sort of like, oh, right. You got to pay attention to the sign change. So minus 2 pi cosine t. Evaluate 0 to pi over 4. Well, we plug in pi over 4, and what do we have? Well, what happens is that pi over 4, cosine of pi over 4, is root 2 over 2. Subtract cosine of 0, cosine 0 is 1. Well, finally, we can multiply the minus 2 through, and since we're multiplying the minus 2, we might as well change the order. So minus 2 times minus 1 would leave us with a 2. Then minus 2 times root 2 over 2 leaves us with a minus root 2. So pi times 2 minus root 2. Nice answer. Beautiful. And it worked out really amazingly nice. Oftentimes, when you see some very complex functions at the start, it's sending a signal. It looks complex, but be careful, be methodical, and things will simplify nicely. When we see nice functions at the start, we know we're in for trouble, because probably what's going to happen is things are going to come to a point where it's like, this is going to be a hard integral to work with, that we need more tools. So it's always kind of refreshing when we see something that looks a little bit intimidating at the start. It's like, okay, something nice is about to happen. Well, we have to do the work to figure out what that something is. All right, well, let's try another one. Now, we'll do another surface area problem. And here we go. Find the surface area, which results from rotating a parametric curve. Log secant plus tangent minus 2 sine t, y is 2 cosine t, around the x-axis. And you're probably thinking, didn't we just do this one? There's a little bit of, it's not exactly the same. If you go back and look, let's see, we have it right here. We can pull it up. You'll see there's a 2 that's been added. Does that do anything? And if it does, what? Well, we've got to find out. But the good news is that a lot of it is still a similar idea. So probably we're going to do things in a similar way. So we have a curve that's doing something. We don't know, but we just sort of draw some wiggly curve. Okay, there's our curve. And same setup as before, right? Where we say, okay, we're thinking of chopping into little pieces, and we're going around the x-axis. So we think about dropping down to the x-axis. And our generic formula, we'll start with our generic formula, says that surface area is going to be adding up, start to finish, 2 pi radius and height. Radius, length. There we go. All right, now, generic formula in place, we're ready to get to work. Radius, pretty easy, right? We're dropping down to the axis again, so our radius is the y value, y of t. So 2 cosine t. Our length, well, length formula for parametric curve, x prime squared plus y prime squared dt. And so that's going to be where we're going to put most of our effort. So let's put in our effort. We got to do the time, right? If you're going to solve the problem, you got to do the time. So we begin. All right, so we have the square root of, take the derivative of x. Well, the derivative of log secant plus tangent, work it out, is secant. So one way you can see it is you just think about, okay, if you think about the integral of secant, it's log secant plus tangent. Another way you just do it is you just put your head down and rush forward and see what happens. Well, log of something is the derivative of that is 1 over the inside. So 1 over secant t tangent t. Derivative of secant is secant tangent. Derivative of tangent is secant squared. And now, if you pull a secant out of the top, you'll see that you're left with a tangent plus secant, which cancels with the tangent of secant downstairs, So it works out. That's why the derivative gives you secant. Okay. Back to our regularly scheduled problem. Derivative of minus 2 sine will be minus 2 cosine. Square that. And then plus y prime for that minus 2 sine. Square that. Okay, so let's proceed. We're going to focus on the expression underneath the square root. We have secant squared. Okay, now we have our cross terms. Secant and cosine cancel each other. So that would become secant times cosine is 1. Don't forget about the minus 2. So that becomes minus 4. Plus, here, 4 cosine squared. Over there, 4 sine squared. Now, what happens to this part there? 4 times cosine squared plus sine squared is 4. Add a negative 4. Cancels. 0. So, what's left is simply the square root of secant squared. Well, that's beautiful. Okay, so now we're ready to do our surface area. It's going to be adding up 0 to pi over 4, 2 pi times the height, the radius, how far we are from the axis, 2 cosine t. Our length, square root of secant squared, is secant dt. And now we say, but wait, cosine and secant, they're reciprocals. So cosine times secant is 1. So that cancels. So it's an even easier integral than we had, right? Because what do we have? The 4 pi can come out, so it's 4 pi, integral 0 to pi over 4, dt. Easy, beautiful. So 4 pi t, evaluate from 0 to pi over 4, and when you plug in 0, you get 0. You plug in pi over 4, 4 pi times pi over 4, the 4's cancel, and therefore we're left with pi squared. That's it. That's the answer. What a great and beautiful answer. You know, you wouldn't think it would work out so cleanly. And then it works out cleanly. Ah, life is good. Life is good. All right. Well, let's do one more. One more problem to finish this up. So, a wire follows the parametric curve. X of t, y of t, is sine of t log 1 plus t squared. And t goes from 1 to 4. Given the density at the point x of t, y of t on the wire is given by delta t equals root t, then set up, but do not evaluate, an integral to compute the total mass of the wire. Now, this is an application. We didn't necessarily go over it, but let's just think about what happens. And we'll figure out how to do it. And of course, we will say this has one of the most beautiful phrases in calculus, but do not evaluate. All right. I love that phrase because that just says, hey, all we need to do is figure out the setup. And that's the most important thing, is the setup. So, what's the picture we should have in mind? What we have is a wire doing something. We don't know. It's not so clear. It's moving. It could be doing, okay, there's our wire. We'll say it's that. Well, what do we want? We want to know the mass of the wire. And what happens is that the mass varies. So you'll notice that as we change time, that the density increases. So you can imagine, well, maybe this is where we're at time t equals 1. And over here, maybe that's where we're at time t equals 4. Maybe. But what happens is that as we go along, it becomes more and more dense. So that it's not very dense at the start, but it gets denser at the end. So we think about, okay, what do we do? Well, we think about mass. Now, how do you do mass in a one-dimensional object? We think of a wire as being a one-dimensional object. So the way we compute mass is we say we're going to add up, start to stop, our density times our length. That's it. That's how you compute mass of one-dimensional objects. density times length. And then we're done. That's the whole thing. And so if we understand what's our density, we understand what's our length, and we know when to start and stop, everything else is, we're done. We've done the whole thing. So here the key is we're not going to think of y as a function of x. We're just going to say everything in terms of time, our parameter. So when do we start and stop? 1 and 4. So we're going to add up from 1 to 4. What's our density? Well, our density at any given time is root t. And what's our length? So here, what do we mean by length? Well, what we always think of, and this comes back to our setup, is we always think of chopping our thing into small parts. So we say, look, find the mass of a little piece. And then we're good to go. So that's what we mean by density times length. What's the density of this little piece? What's the length of this little piece? Density is root t. The length is the distance formula. So square root of our x prime, so take the derivative of sine, will be cosine squared plus take the derivative of y. Well, whenever we take a derivative of a log, do 1 over the inside, so 1 plus t squared, times the derivative of the inside, which goes on top. So it's the function on the bottom, derivative of the top. That's how you take the derivative of a log of a function, squared dt. So density, length. That's the mass of a little piece. Add it up. That's the total mass. And we've set it up. And looking at this, I think we're going to be pretty happy we don't have to integrate, because that does not look like something we'd want to integrate. But the moral here is that if you understand how problems go, the generic setup, we can adapt to our new parameterized versions fairly straightforward. See here, we've talked about mass of wires before, so we knew how to do it. We said, well, what's the mass of a little piece? What's the length of a little piece? Multiply that. What's the density of a little piece? What's the length of a little piece? Multiply. That's the mass of a little piece, and add it up. The same principles hold. The same principles hold. Which is why this is so much easier to work with. Because now you can handle the parameterized version versus just say what happens with a straight rod versus what happens along a curve. It's all one generic formula. Wow. It's great. Beautiful stuff. All right. Well, thanks for coming and for doing some practice with me. Hope you have a great day.